Lesson 80. In this lesson, we will revisit kinematics, which is the study of motion using calculus. So let's start by recalling what we know about the relationships between position, velocity, and acceleration. All of these quantities are called vector quantities because they involve size, like how fast, how long, how quickly the speed is changing, and with the direction. So from position to velocity, we know that velocity is the rate of change of position, which means that they have a d by dt, a derivative kind of relationship. So we can say that v of t is s prime of t, and a of t acceleration is the rate of change of velocity, therefore it is v prime of t. Now we know the relationship between, taking a derivative and taking the antiderivative, or when we're integrating a function, what happens, right? So if I have to go from acceleration back to velocity, I will have to integrate at, right, to get v of t. And again, to go from the velocity function to the position function, I can also take the integral of v of t and find s of t. Also, as a warm-up, here is a graph that shows the velocity of a particle moving along the x-axis from t equals to 0 seconds to 10 seconds. At the beginning, when t is 0, the initial position of the particle is 3 meters to the right of the graph. Okay, so we would like to describe the motion of this particle by completing the table below. So you can pause the video, take some time to fill out, the sign of velocity. We're interested in whether velocity is positive, 0, or negative. You're actually going to calculate the displacement of the particle in each interval and the distance from the origin at the end of the time interval. So there's a difference, right? Because the distance, you're always trying to count it from the 3 meters to the right of the origin position. Okay, so let's pause the video now until you have finished filling out the chart. Okay, so I hope you have completed the chart like I did. And to recap, basically velocity is reading the sign of the graph, whether the graph appears above the x-axis at 0 or below the x-axis. And when we calculate the displacement, we're simply looking at how far the particle has traveled and in which direction during the time interval by calculating the area. Any area above the x-axis, or the time axis, I should say, is positive. Any time or any area that is below the t-axis is negative. So displacement has direction, therefore has plus and minus signs. When we calculated the distance from the origin, however, we're considering how far you have moved at the end by the end of each time interval. So starting at 3 meters, in the first time interval from 0 to 2 seconds, the displacement is 4 meters forward. So that means in total, you are 7 meters away to the right of the origin now. And then you start accumulating these displacement up until time equals to 4 seconds. And you notice that in the next interval, 4 to 6 seconds, the area between the graph and the t-axis is negative. So you're going backwards, right? So from the 9 meter mark, you're actually going back 2 meters, which means that your new position by the end of that time interval is 7 meters and so on, okay? So hopefully this chart or this exercise has helped you to recap your understanding of kinematics, and it will take you to the next page, which is an investigation found in your textbook on page 528. In this investigation, you will find a relationship between how you can find the displacement versus the total distance of a particle when you're given the v of t function. When you're done, you can go to part 2 of this lesson's videos. Lesson 80. So hopefully from the investigation, you have discovered that in order to find displacement and total distance from the velocity function v of t between times t1 and t2, the only difference is that because displacement involves positives and negative so-called directions, then you can simply take the definite integral of v of t with respect to time from t1 to t2. The adjustment that you need to make to calculate the total distance, which is really the path length, so I ignore whether I went positive or negative in directions, is that I can take the definite integral of the absolute value of v of t with respect to time from t1 to t2. We're going to practice using these ideas in the examples below. You will need your graphing calculator or at least Desmos. Example 1. The velocity function of a particle moving along the x-axis is given by v of t and the time interval between 0 to pi over 2. First, we're going to sketch the velocity function and find the times when the particle stops, moves to the left, and moves to the right. Okay, so I have made this graph on Desmos, and we see clearly that in this particular velocity function, the three zeros happen at 0, 0.8295, and 1.5484. Okay, so let's remember that. So let's put the sketch on the lesson. And be careful because you do have an endpoint. And then from previous work that I have done, or you can go back to your graph and do a trace. This is 0.387 as the y value. The first 0 is 0.83. Second 0 occurs at 1.55. This is time. This is v of t. Okay. So we can say that the particle stopped. That's when v of t equals 0. At t equals 0 seconds, 0.83 seconds, and 1.55 seconds. Okay. When is it moving to the left? Well, we'll assume that positive is right and negative is left. So it's moving to the right when the velocity is positive. That means that it's from 0 to 0.83. And to the left, when v of t is less than 0, between 0.83 and 1.55, but then it's go back to moving to the right, so 1.55 t and pi over 2, because we do have a cutoff. Okay. Part B, the particle's displacement at the end of the pi over 2 seconds. So here we know that displacement can be calculated by taking the integral of the function t squared cosine t cubed plus 1 dt from 0 to pi over 2. So let's work this out. Okay, I'm taking cosine of t cubed plus 1, and this whole function is multiplied by t squared. So the two so-called polynomial functions are off by 1 degree. So I know that a substitution here can work. du is 3t squared dt. So that means I can divide by 1/3. And then, well, these are x values for pi over 2. And then if I change it in terms of u, 0 cubed plus 1 is 1. Here I'm just going to call this pi over 2 cubed plus 1, whatever that gives me. And then I have cosine of u du. All right. So 1/3, the integral of cosine is sine. u, and I have going from 1 pi over 2 cubed plus 1. Okay, and if you wish, you could also do this on your calculator because you're allowed in this case. Remember, going to math and then number 9 helps you to find a definite integral. It works out to about negative 0.609 meters. Okay. In part C, we are looking for the total distance this particle has traveled in the time interval instead. So remember, we only need to make one slight adjustment, which is to take the same definite integral but the absolute of the function v of t. Okay? You can actually do this directly using your calculator. To insert an absolute value symbol, you will have to go to the math function. Let me write this down. Okay, and then you scroll over to the number menu, and then the first option is abs. Okay, this allows you to insert an absolute value symbol on your graphing calculator, on a TI-84 at least. Okay, and when you sub in everything properly, you're going to get 0.724 meters. And this is 3 sig figs. This is also 3 sig figs. Okay. Here is example 2. A stone is thrown vertically upward with an initial velocity of 2 meters per second. If the acceleration is 9.8 meters per second squared down, find A, the total displacement, and B, the total distance traveled when the stone falls back to the ground. Okay. So either way, we need a function here, right? We need the velocity function. And let's list out what we know so far. We know that v of 0, the initial velocity, is 2 meters per second up. And acceleration, a of t, because it's constant, is negative 9.8 meters per second squared, because the negative indicates it's down. Find the total displacement, and we are looking for, first, v of t, which allows us to find out, what total displacement and total distance traveled is. But there's one other thing that we also need to know, which is what is the initial and final position, or the time it takes, right, for the stone to hit the ground. What we do know, however, is that the total displacement, we can even answer this right away, is that the stone started from the ground, so S of 0 is on the ground. S of T2, the final, is also on the ground. So what is the total displacement? Of course, it is 0 meters, right? Because it has not changed position. Okay, so we have that down pack. Next, let's start by looking for v of t. All right, so v of t, I know is given by taking the integral of a of t dt. I have the integral of negative 9.8 dt, which gives me negative 9.8 t plus c. Now we need to figure out what c is equal to by subbing in v of 0 equals to 2. 2 is equal to negative 9.8 times 0 plus c. So c must be 2, which results in the following. V of t must be negative 9.8 t plus 2. Now we're going to find S of t. Which is the integral of negative 9.8t plus 2 dt. So I know that this is going to give me negative 9.8 t squared over 2 plus 2t plus c, which is negative 4.9 t squared plus 2t plus c. The problem is, well, what is c? Once again, we can make use of the initial condition, which is 0 meters. Well, when you sub in 0 into S of t, c is going to be 0. Therefore, at least we know that S of t is equal to negative 4.9 t squared plus 2t. So now I have a position function. Why is this useful? Well, because I need to know how long that stone was in flight in order to find the actual total distance, correct? So we know that the change in position from 0 to 0. If I make a rough sketch to get the idea straight, S of t and t, well, I know that S of t is really t times negative 4.9 t plus 2. So I have 1 0 here, another 0 somewhere here, and then it went up and comes back down. It's a parabola, opens down, it's symmetrical. Everything's good, right? So I need to know what time this is by solving this equation. By setting this equal to 0. All right. Well, clearly, the first 0 occurs at t equals to 0, or the second 0 occurs at 2 divided by 4.9, so it's roughly 0.408, which then we can now calculate the total distance by taking the integral from 0 to 0.408 of the velocity function, negative 9.8 t plus 2 dt. All right. And not only that, but to be safe, it should be an absolute value of that. Okay? So now you can use your graphing calculator again to evaluate this number, and it will give you 0.408 meters. Okay?